And this lesson, we're going to start by talking about light, and then we're going to show eventually, if you just hang in there, the relationship between light and the location of electrons in an atom. So now, last time we said that the electrons are found outside the nucleus. So we're going to get a little bit more specific as we go through this unit and describe more specifically where the electrons are outside the nucleus, because they're not just randomly outside. And so we'll get to that. And in order to really get a better understanding of where the electrons are, we need to understand the properties of light. So light consists of waves, has wave-like properties, also has particle-like properties. So on this line, let's draw a wave. And then let's discuss the properties of waves. First one, the distance from identical spots on a wave, meaning from the top of one, say, to the top of the next wave, or bottom of one to the bottom of the next. This is called wavelength, the distance between 2 points on the wave, wavelength. Wavelength of light is usually measured in angstroms. The symbol for an angstrom is a capital A with like that circle on top. Make a note, an angstrom is 10 to the negative 10th meters. Wavelength is sometimes also expressed in nanometers. I believe your book gives the wavelength of light in nanometers. Remember, a nanometer is 10 to the negative 9th meters. So angstroms 10 to the negative 10th, nanometers 10 to the negative 9th, or a billionth of a meter. When we're using wavelength in a mathematical equation, we often symbolize wavelength with the Greek letter lambda. So it's kind of like an upside down Y. So this is called lambda, L-A-M-B-D-A, lambda. The other important property of a wave is something called frequency. Frequency is how often a wave passes a given point per second. So think about like waves in the ocean. How many waves hit the shore every second? That is the frequency. Frequency is usually measured in per seconds, we say. So that's 1 over a second, or s to the negative 1, which is the same thing as a hertz. So maybe you've heard this before, like computer microprocessors being so many gigahertz or terahertz. And so hertz is a unit of frequency, same as per second. Symbol for frequency, if you're in physics, the symbol makes sense. It's an F. This is chemistry, so the symbol is a Greek letter called a nu, Greek letter nu. Kind of looks like a V. Third property of a wave is amplitude. Amplitude is simply how high a wave is. Amplitude has nothing to do with wavelength or frequency. We'll see in a minute, though, that frequency and wavelength, though, are related to each other, and you need to know that relationship. All right, so go ahead to turn to page 96 in your textbooks. There's something there known as the electromagnetic spectrum. It shows all of the different types of electromagnetic radiation or light. So that term light doesn't mean just the stuff that comes out of the light bulbs. Light is a general term for electromagnetic radiation. There's different types of light. There's visible light, that's the light we can see. There's UV light, infrared, gamma radiation, X-rays. These are all types of electromagnetic radiation. And so take a look at the scales on there. So on the top we have wavelength, which is given to us in meters. And then we have frequency, which is given to us in hertz. As you go from left to right, so from radio waves to gamma rays, what happens to the wavelength? So we have radio waves about 10 to the second meters, gamma rays 10 to the negative 14th. So going left to right on this electromagnetic spectrum, we see that the wavelength decreases. Now take a look at the bottom scale, the frequency. Going again, same direction, left to right, starting with radio waves, frequency of about 10 to the 6th hertz. And then gamma rays, frequency of about 10 to the 22nd. So we see that as frequency goes up, what happens to wavelength? Wavelength goes down. What do we call this type of relationship where if one quantity increases, it causes the other quantity to decrease? The name for that is inversely proportional or inversely related. So wavelength and frequency are inversely related. How about this then? Mathematically, how do we show in an equation if two variables are inversely related? Well, let's go back to something else that is directly related. Directly, remember, goes the same direction. Mass and volume are directly related. Do you remember the equation for density? Where are mass and volume? Well, in this case, we have a ratio between mass and volume. The ratio of a substance's mass to its volume is constant. So that's for directly proportional variables. Here we're talking about inversely. If two variables are inversely related, their product, what does that mean mathematically? Products, multiply them. Their product is equal to a constant. So here's the equation that shows the inverse relationship between frequency and wavelength. So C equals lambda nu. So of course lambda is our wavelength. Careful, in meters. It's not going to be given to you in meters. It's probably going to be given to you in nanometers, and then we need to convert it. Nu is the frequency in per seconds. So if it's given to you in hertz, just plug into the equation per second, 1/second. And then C is a constant called the speed of light. The value of the speed of light in a vacuum is 300 million meters per second. So you need to memorize that value. 3.00 times 10 to the 8th meters per second. So again, inversely proportional. As wavelength goes up, frequency goes down, and vice versa. Were you aware that X-rays are dangerous to us? This is why when you go to the dentist, they put that heavy lead blanket on you to protect your body from the X-ray radiation. Well, gamma rays are even more dangerous. So again, go back to the electromagnetic spectrum on page 96 and see where X-rays and gamma rays are. Gamma rays are the most energetic form of electromagnetic radiation. So what I'm trying to get at here is, what is the relationship between frequency and energy this time? So we see that frequency increases left to right, and I just said that gamma rays have the most energy, so that tells us then that the relationship between frequency and energy is direct. So it says the energy of a single photon of light is directly proportional to the frequency of the light. So again, let's write a mathematical equation showing the direct relationship between energy and frequency. It looks like this. Where E is the energy of a single photon in joules. Frequency, still nu, that's in per seconds. And then we have a proportionality constant called Planck's constant. It just turns a proportion into an equality. And so H is Planck's constant. Again, another value that you need to memorize. 6.63 times 10 to the negative 34th joules seconds. Joules times seconds. So go ahead and take out your calculators and let's do some calculations. I'll do one for you. All right, it says calculate the frequency of red light if it has a wavelength of 650 nanometers. Better yet, why don't you try this? So we know the we know the wavelength, we know the speed of light, that's a constant. Take that equation, C equals lambda nu, rearrange it, solving for nu, the frequency, and see what you get. All right, we'll compare the results. Please pause the video. So let's check to see how you did. First of all, did you rearrange the equation to isolate the unknown variable, nu? You should. This is what I've been talking about for the first few lessons in our units where we have calculations. So we have C over lambda equals nu, plug in our values, and we have a problem. Take a look at the units. What do you notice? Here we have meters, here we have nanometers. Those need to cancel. We want to be left with per seconds. So take that wavelength in nanometers and convert it to meters. Remember, there are a billion nanometers in a meter, or a nanometer is 1 billionth of a meter. See what you get. Convert that. Pause the video, please. So to convert from nanometers to meters, take your wavelength in nanometers, divide it by a billion, which is 1 times 10 to the 9th, And we end up with 6.5 times 10 to the negative 7th. Is that right? Notice here, no decimal. So 650 nanometers, that's 2 sig figs. So we convert to scientific notation here. It's 6.5 times 10 to the negative 7th. Meters cancel. We're left with per seconds, which is the same thing as a hertz. 4.6 times 10 to the 14th hertz. Number 2, calculate the energy this time of a single photon of red light, the same one, with a frequency calculated in number 1. So again, this time we know the frequency, we know Planck's constant. Go ahead and use those to calculate energy. Please pause the video and do that now. So notice when I plugged in the frequency, I did not plug it in hertz, I plugged it in per seconds so that the units cancel. Remember, this is the same thing as a 1 over a second. So that cancels there. We're left with joules, 3.0 times 10 to the negative 19th joules. Now, usually we're talking about things giving off more than just one photon of light. Photon is just a particular bundle of light, is called sometimes. It's just like a certain quantity. And so this one's a little bit different. It says, how much energy would 1 mole of photons of red light possess? Let me give you this relationship. One mole of photons is 6.02 times 10 to the 23rd photons. So let's go back to that last example. I'm going to change the units a little bit. So it says joules. I'm going to put joules per photon. That's the amount of energy per every 1 photon of light that's given off by something. So this next question is, how much energy would 1 mole of photons of red light possess? So we're going to take that 3 times 10 to the negative 19th joules per 1 photon and convert that to joules per mole. Let me show you what that looks like. If you want to try it out, go for it. Pause the video. So notice here we got photons on top. That's going to cancel the photons on the bottom there. This is called the conversion factor. We'll learn formally how to do those later. So you get 180,000 kilojoules per mole. Remember, we want 2 sig figs. And then I just took that big number in joules and converted it to kilojoules. So we get 180 kilojoules per mole, or 180,000 joules per mole. So what is the relationship between light and the location of electrons in an atom? So we're going to link the two together now. So let's do this. Let's draw a model of an atom. When I say draw a model, do you know what atoms will look like? Maybe in elementary school, middle school, you drew something similar to this. So we have the nucleus at the center. And then we have these circles or rings that go around the nucleus. This is known as the Bohr model. And this is going to help us to understand the relationship between light and where the electrons are outside of the nucleus. By the way, the Bohr model is an absolutely terrible model of an atom. Atoms don't look like this. First of all, this is a 2-dimensional model trying to represent something that exists in 3 dimensions. So that's probably its biggest downfall. Notice anything about those circles or rings around the nucleus? Again, the nucleus is in the center. Yeah, they're not the same distance apart from each other. So I tried to show it that way on purpose. Probably could have done a little better job, but did the best I could here. All right, so what does this model tell us about an atom? This shows very clearly something about where the electrons are in an atom. Here's what this shows. This model shows that the electrons exist at very certain and specific distances from the nucleus. So for example, an electron could be this far from the nucleus, or it could be this far, or this far, or this far, or this far, and nowhere in between. It's only at certain distances from the nucleus. Here's the analogy I like to use. kind of like a ladder. So let's say you have a ladder. First of all, let me jump ahead a little bit. We have this thing called potential energy. And the important part here is the H. So things that are attracted to each other that are separated by a certain distance, or in this case, H height, have potential energy. So the relationship between height and potential energy, they're directly related. So let's do this. If you're on this first step here, you're a certain distance from the ground. You have a certain amount of potential energy. Now, can you stand anywhere between two of the rungs on the ladder? No. You can either be this far from the ground, or this far, or this far, or this far, or this far only. You can't stand between two rungs. So you have, when you're standing on a ladder, a certain amount of potential energy. You can only exist at a certain distance from the ground. Same thing with electrons and atoms. They're attracted to the nucleus. They have a certain amount of energy associated with them, very specific, based on their distance from the nucleus. So again, what this model does a really, really, really good job of is showing us that electrons exist at specific distances from the nucleus. Very, very, very important. These distances from the nucleus are known as principal levels or energy levels. I usually use the term energy level. So it says each ring around the nucleus is called an energy level. The closest one to the nucleus is labeled 1, or the first energy level. The next one is 2, or the second energy level, 3, and the third energy level, and so on. Just like as you go up on the steps on a ladder, the further an electron is from the nucleus, the more energy that it possesses. So electrons further from the nucleus possess more energy than electrons that are close to the nucleus. Each of these rings, sometimes called shells or energy levels, we really call them, can hold only a certain maximum number of electrons. And we can determine that by 2n squared, where n is the principal number. So for example, how many electrons maximum can fit in the first energy level of any atom? Well, first energy level, n is 1, so make sure you do PEMDAS here, so exponent first. 1 squared is 1 times 2. First energy level can hold a maximum of 2 electrons. Second energy level can hold a maximum of how many electrons? Give me that number. N is 2, 2 squared is 4 times 2, 8 electrons. Third energy level can hold a maximum of how many electrons? That would be 18, okay? Something else very important, electrons in atoms usually occupy the lowest energy level available. When an atom has all of its electrons in the lowest energy level that is available, it is said to be in the ground state. So, just like you, when you wake up in the morning, you're the lowest energy state possible, you are in the ground state, and hopefully don't stay that way throughout the day. If electrons receive an input of energy via heat or electricity, and I'll show you examples of both, the electrons, it says the electrons move away from the nucleus to a higher energy level. Any atom that has one or more of electrons in an energy level higher than in the ground state, so I changed up the wording a little bit there in the notes, higher than in the ground state is said to be in an excited state. Kind of like you in the morning. Let's say you wake up, you're tired, low energy, ground state, and you eat a whole bunch of sugary foods. What happens? You get excited. You have a lot of energy. Do you stay that way? Probably not. Same thing with these excited atoms. So electrons can be bumped up to higher energy levels, but they don't stay there. Eventually, those electrons are going to come back down to a lower energy level. Maybe not the one that they started at, but it's going to come down, maybe stepwise. Here's the important part. It says when an electron in an excited atom falls down to a lower energy level, the energy that it loses during this fall is given off as light. The further that electron falls, the higher the energy of the light given off. So if we have these atoms that are giving off certain colors of light, if you go back to the electromagnetic spectrum on page 96, visible lights, the different colors of visible light, which are these, have different amounts of energy. By the way, which color of light has the lowest energy? Remember, we talked about the relationship between frequency and energy earlier. So it's got to be red or violet. It's red. What color of light, visible light this is, has the highest energy? That would be violet. And so some atoms give off different colors of light, which tells us about where the electrons are outside the nucleus in terms of how far away they are from the nucleus. Go to page 97, and I'm going to see if I can show you this in my classroom. So what I have a glass tube. Let's see if I can make this bigger. I have a glass tube filled with some gas. And I'm going to put this in a device that sends electricity through this gas. And what that electricity is going to do is it's going to cause the atoms to become excited. It's going to bump up electrons to higher energy levels. But again, those electrons don't stay there. When the electrons go back down to a lower energy level, they're going to give off light. Let me show you. So I know it's hard to see, it's in the dark, but what I have here is a gas tube filled with hydrogen gas. I'm going to turn on the switch and send some electricity through that sample of gas, cause those atoms to become excited, and what do we see? Light is given off. Those excited atoms give off light, and it's kind of a pink color. Now, if we pass this light through a prism, you would see what you see in the book. Let's take a look at that figure again in the book. So a prism is able to separate light into its colors. Now, what do you notice? We see that the excited hydrogen atoms only give off certain colors of light. They give off photons of red light, photons of kind of green, blue, and violet. And it shows there in the book the wavelength of those photons of light that are given off. Only those. Now, how about this? If the electrons in an atom can exist at any distance from the nucleus, what colors of light would be given off from excited atoms? Let me say again. If the electrons could be anywhere, any distance from the nucleus, what color of light would excited atoms give off? Pause the video if you need to think about that. What we see here in the book on page 97 is called a line spectrum. Only distinct colors of light given off. If electrons could exist at any distance from the nucleus, we would see a continuous spectrum, kind of like what we see on page 96. All the colors of light representing all the different energies possible for visible light. That's not what we see, so that tells us that the electrons aren't just anywhere outside the nucleus, they exist at specific distances from the nucleus. Now, where have you seen this phenomenon before? Where you add energy to atoms and it causes them to give off light. Pause if you need to think about it. Have you ever seen a blacksmith work? Take a piece of iron, put it in the fire, leave it in there for a while. What happens to the iron? When you take it out, it's giving off light. You know why? Because those iron atoms are excited and they've been bumped up to a higher energy level. They don't stay there. They come down, and when they come down, they give off light. Also, some of you may have a stove that has like a metal coil on the top. I don't think your book has an example. My other textbook shows an example of that. You may know what I'm talking about. It has a coil, and when you turn it on high, that coil turns red. Again, same idea. Or in the case of this hydrogen tube I showed you. Neon lights. This is how neon lights work. You have neon gas inside of some glass tube, pass electricity through it, and it gives off light. By the way, what color are neon lights? Pause the video to think about it. Let me show you what color neon lights are. So this time, instead of hydrogen in here, I have neon. Let me turn on the power and see what color neon lights are. It's pretty close. Can you see that? Neon lights are red. They give off red light. Now, perhaps you thought neon lights give off green and yellow and orange and blue light. That's not true. Neon lights, sometimes they're called collectively, if they don't give off red, guess what's not inside them? It's not neon. If it's a red neon light, then it is truly neon. So, the other day, here's where we were. The electrons are found somewhere outside the nucleus. Today, a little bit more precise, not just anywhere outside the nucleus, but at specific, certain distances from the nucleus in these things called energy levels. By the way, anytime I use that term energy level, what must pop in your head is distance from the nucleus. The higher the energy level, the further that electron is from the nucleus. All right, we will continue next time with being more precise. Not just outside the nucleus, but where outside the nucleus are the electrons. Thanks for watching.